For decades, we've looked at the 10-second electrocardiogram as our go-to for arrhythmias and ischemia. It's a cornerstone of cardiology. But what if, hiding in plain sight within those familiar waveforms, there's a much deeper story? A story about a patient's entire metabolic future. Well, that's exactly what we're digging into today. A truly groundbreaking study that uses AI to pull a brand new biomarker for cardiometabolic risk right out of a standard ECG. So here's our game plan. First, we'll quickly touch on why BMI, our old standby, just isn't cutting it. Then, we'll get into the cool part, how an AI was trained to see body composition in an ECG. The real breakthrough, though, is a new biomarker they've called delta BMI, and we'll unpack the deep biology that makes it work. And finally, we'll bring it all home and talk about what this looks like in the clinic. All right, so body mass index. We all use it every single day. It's simple, it's fast, but let's be honest, as clinicians, we are all painfully aware of its limitations. It's a starting point, sure, but it so often paints a blurry or sometimes just plain wrong picture of a patient's actual metabolic health. And this quote from the paper just nails it, doesn't it? BMI has no idea if it's looking at a muscular athlete or someone with sarcopenic obesity. More importantly, it can't see that dangerous visceral fat packed around the organs. This is exactly how we get that metabolically obese, normal weight patient who walks out the door thinking they're fine when they're actually a ticking time bomb. So this is the big what if that drove this whole research project. What if the heart's electrical signals, which are, of course, shaped by the entire body's composition and metabolic environment, could give us a much smarter, more nuanced view of risk than just dividing weight by height squared? So, the researchers had this hypothesis that a deep learning model could be trained to pick up on these incredibly subtle electrical signatures. They pointed this AI at the standard 12-lead ECG with one very clear goal: predict a patient's BMI using nothing but the raw squiggly lines. And the scale of this was massive. They used a residual neural network, a ResNet, which is fantastic for complex signal data like this, and fed it over 500,000 ECGs from one cohort. But here's the crucial step. For all of us who care about robust science, they then validated it externally on a totally separate population, the UK Biobank. No overfitting here. This was the real deal. So, how did it do? Honestly, these numbers are seriously impressive. An R-squared of 0.43 in the training set and 0.39 in the validation set is really strong. I mean, to put that into perspective, it's right up there with models trying to predict BMI from structural brain MRIs. It just goes to show you how much information is actually hiding in the ECG. But here's where this study goes from interesting to truly paradigm shifting. The point was never just to create a complicated way to guess a simple, flawed number. No, the real magic happened when they started looking at the difference between what the AI predicted and what the scale actually said. And they called this delta BMI. Think of it this way. If your delta BMI is positive, it means your heart's electrical signature looks like it belongs to someone with a higher BMI than you actually have. Your heart is broadcasting a signal of a higher metabolic burden. It's a direct readout of that discordance between your body's outward appearance and its inner metabolic state. Okay, so this is the million-dollar question, right? We have this new number, this delta, but is it just a neat academic curiosity, or does it have real teeth? Does it actually predict hard outcomes, even in people whose measured BMI looks perfectly fine? The answer is a resounding yes. In the UK Biobank, people with the highest delta BMI had a more than twofold, 2.28 times greater risk of developing type 2 diabetes down the road. And here is the absolute killer point. That's after adjusting for their actual measured BMI. This is a completely new, independent signal of risk. And you can see here, this is not just a one-trick pony for diabetes. Look at the hazard ratios across the board for that top delta BMI group. The risk is consistently and significantly elevated for the whole spectrum of cardiometabolic diseases, hypertension, lipid disorders, you name it. The ECG is clearly tapping into a common, underlying pathophysiology. Now, for an academic and clinical audience like us, a strong statistical signal is compelling, but it's not enough. We need to ground it in biology. We have to understand the why. So the researchers did their due diligence and went on a deep dive with a full multi-omic validation. First up, the Phenome-wide Association study. And what did they find? Well, a high delta BMI was linked to, surprise, surprise, a textbook list of cardiometabolic red flags.
more truncal obesity, more fat around the heart, that classic atherogenic lipid profile, and an inverse link with SHBG, a known marker of insulin resistance. Check, check, and check. But they went deeper. The metabolomic and proteomic data tell a beautifully cohesive story. High delta BMI is linked to metabolites like valine and, of course, glucose. And on the protein side, it's associated with higher levels of things that inhibit insulin release, like syntaxin-3, and lower levels of things that help insulin sensitivity, like adiponectin. It's all pointing to the same pathway. And then, the final piece of the puzzle, the genetics. The genome-wide association study connected the dots completely. They found genetic links between delta BMI and genes that regulate the ECG signal itself, like SCN1A, and genes that regulate metabolic function, like CASC20 for waist circumference. It's the smoking gun, a clear genetic bridge between the electrical signal and the metabolic state.
Okay, so the science is rock solid. We've geeked out on the stats and the omics. But what does this all mean on a busy Tuesday morning in the clinic? How do we actually translate this incredible finding into something that helps our patients? Let's make this super practical. Imagine two patients walk into your office. Both are 50, both feel fine, and both have a healthy BMI of 24. On the surface, they're identical. But when you run the routine ECG, the AI-enhanced report comes back. Patient A has a low or negative delta BMI. Patient B has a high, positive delta BMI. Now, who are you more worried about? Who gets the more aggressive talk about diet and exercise? Who are you going to screen more closely with an HbA1c? It's unequivocally patient B. Even though their BMI is normal, this delta BMI signal is a huge red flag that tells you their underlying risk is more than double. It allows you to intervene before they become a statistic. And the beauty of this is how seamlessly it could fit into practice. We're not talking about some new, expensive scanner. You do the same 12-lead ECG you always do, the algorithm just runs in the background. And boom, you get an enhanced report with a new layer of risk stratification. It makes personalized prevention a real, tangible thing, moving us beyond these crude one-size-fits-all guidelines. So let's just boil this all down. We have delta BMI, a potent new biomarker that we can get from a test we already perform every day. It's a powerful predictor of future disease, totally independent of measured BMI. Its biological underpinnings are incredibly solid, and it gives us a real, practical tool to get smarter about personalizing risk for our patients. You know, this work is so much bigger than just one biomarker. It's a proof of concept for a whole new way of thinking. It forces us to ask, what other secrets are lying dormant in all the routine tests we run? As AI gets better and better at finding these hidden signals, what other fundamental clinical metric is about to get a complete redefinition? It's a really exciting time to be in medicine.